You can start.
Okay, yeah, thanks, Lucy. Thanks, Brian. And we also have Uther and the Sierra support team here, all our engineers. So please ask questions. I always say this, but it helps us get better. It helps us understand what you guys are looking for, and then also you'll get good answers, not just from me or Brian, but also from Sierra's engineering staff like Uther. Uther's in charge of our engineering, so it's great that he's on as well. All right. So 2 sentences about Sierra. If you haven't already requested a quote from us, we do PCB fabrication and assembly and also supply chain management. And our markets are traditionally industrial, medical, aerospace, where the board is critical. And we also have our online e-commerce, which is meant more for standard products. So if you haven't gotten a quote from us, please do so. That helps fund our wonderful educational material for all of the engineers out there. Okay, so this is the title of the presentation, what we're going to be covering. Basically transmission lines, and then Brian has great practical information at the end and demos and all of that. So I'm really excited to have that as well in this webinar. So again, why uniform impedance is crucial for transmission lines. So inconsistent line impedances cause signal reflections and EMI, all which are not good. So getting this right really will make an impact on you and your what your company is trying to do. And of course, high-speed signals are critical, and they need proper timing. And when you have a good impedance, you'll get consistent signal travel, preventing your synchronization errors. And the impedance mismatches can also cause power losses. So you'll improve your power efficiency and basically better health overall for your PDN. And so Sierra is going to try and do more webinars on PDN, because that's becoming a very important topic for lots and lots of engineers.
Yes, we'll be doing a webinar on PDN with Steve Sandler in Q2.
Thanks. So that's great. So good to hear. So, this is why control impedance is, so super important. Some interesting facts, which I'm going to skip over. And then, just the idea of showcasing the structures, microstrip, strip line, coplanar. So this is a reference of what we're, speaking about, in different structures you can have. So you want to look at your signal speed and propagation delay. And in microstrips, the signal trace will run along the top surface of the substrate, and the ground plane is on the bottom. So the signal partially propagates through the dielectric, so resulting in a lower effective dielectric constant compared to other geometries. So microstrip lines generally have a higher signal speed and a slower propagation delay. And for the same trace width and spacing, you need to have slightly lower signal speeds and greater propagation delays. And in the strip line configuration, the signal travels.
Just, Amit, on the microstrip, the signal is on the outer layer, and the ground plane is just the layer next to that. Okay, not at the bottom. Okay, yeah. I just wanted to make sure.
Okay, thanks.
Yeah.
Here's a chart which shows the dielectric constant effective dielectric constant, signal speeds, propagation delays in these different structures, microstrip and strip line, for a few different materials. And these materials are very commonly used at Sierra and I think around the world, really. Next, we talk about this concept of critical length. So the trace length, the critical length is the trace length above which the trace has to be designed as a transmission line with control impedance. So you can use these formulas to understand what is the critical length for analog and digital signals. And so the idea is that, you know, when does this become critical, you should know. The short lines may not be critical. Next is signal rise time. You need to know the data transfer rate and the clock frequency to calculate the signal rise time. And so you can compute the signal rise time with these formulas. We have a better way to do this. And I think we're going to do a demo for that. Is there someone to do the demo?
Yes, sir.
Okay, thanks.
Hi, everyone. So this is a Sierra Circuits bandwidth rise time and critical length calculator. This helps you to calculate the signal wavelength and most importantly, the critical length or the short length of the selected geometry. So we have three types of geometry over here in the dropdown: the uncoated microstrip, coated microstrip, and the strip line. Let's go with coated microstrip for now, and you can see that the representation or the geometry image has been changed accordingly. Let's enter the input parameters. Let's go with a dielectric constant of 4. And then we have maximum data transfer rate, faster signal rise time, maximum frequency content, and the 3 dB bandwidth over here. And you can choose any one of these 4 parameters as your input parameter, and the other 3 will be calculated. Let's go with maximum frequency content for now. And to choose that, you just click on this tick box here. And you can enter the value. Let's go with 10 gigahertz and click on calculate. The DTR, fastest signal rise time, and the 3 dB bandwidth are calculated and displayed over here, along with the wavelength, critical length, and the maximum short length. So transmission lines in any high-speed design should be uniform to avoid signal distortions and crosstalk. Trace parameters like bandwidth, rise time, and the critical length can affect impedance matching, which influences the overall performance of the board. Hence, the analysis is one of the key steps in high-speed designs. Thank you.
Okay, thanks, Vandana. Share my screen again. Okay, so insertion loss. So insertion loss in PCB transmission lines refers to the overall decrease in the signal strength as the signal travels through the entire transmission line. And it's the sum of all the individual losses experienced by the signal. So conductor loss, dielectric loss, radiation loss. And we'll just touch on each one of these. So conductor loss or copper loss refers to the decrease in signal strength as it travels through the conductor. And a weakened signal can be more susceptible to picking up noise and interference during transmission. So this can compromise the overall circuit performance and data integrity. So to compensate for this, circuits may require signal amplification and consume more power. More power equals more heat. More heat equals a higher board temperature. Dielectric loss is the energy lost when a signal travels through the insulating material. And so at higher frequencies, the electric fields associated with the signal changes more rapidly. Therefore, the molecules in the dielectric vibrate more vigorously and dissipate more energy as heat. So also the loss increases with the higher dissipation factor values. Radiation loss refers to the phenomenon where electromagnetic energy is emitted into free space from the traces. As the signal frequency increases, the wavelength decreases and the transmission line may behave like an antenna radiating energy into space. So uncontrolled radiation can interfere with other electronic devices, causing malfunctions, etc. You're not going to pass EMC. Leakage loss is also another radiation loss that can occur during current flow through the dielectric material, and even small leakage currents can contribute to a noticeable signal loss at very high frequencies. So here's an example of loss comparisons. So also something to be aware of is how solder mask can affect your insertion loss. So the strip line structure is buried between the substrates, hence it doesn't experience much signal degradation due to solder mask. However, microstrip and coplanar structures have exposed signal traces in the outer layers, and if you coat the exposed copper with a mask, some fields will also pass through the coating, and the dielectric loss will increase as the coating material's dissipation factor is approximately 0.025. So for high speed and RF components, avoid solder mask if possible. If this is not possible, consider solder mask constant, the dielectric constant, to calculate your effective dielectric constant. And as a separate note, if you put down on your fab drawing a minimum of 1 mil of solder mask, most fabricators that pay attention to the note will put down 2 coats of solder mask to ensure this. So you'll be getting more than 1 mil. So just use that as a reference. So techniques to design PCB transmission lines with controlled impedance. So to reduce the skin effect losses at high speed frequencies, you can employ various low profile copper foils, such as very low profile, reverse treated foil, and ultra low profile. So all these foils are special order. You have to specify them on your fabrication drawing. So you can also select substrates with high volume resistivity to minimize the leakage currents. And you can choose materials with a dielectric constant of less than 4 and a dissipation factor of less than 0.005. Some stack-up strategies to reduce the dielectric losses. So first, place your signal layers, 1 dielectric, away from the reference plane to enhance the noise suppression. Position your RF traces and components on the external layers to ensure consistent impedance. Finally, group your signal layers based on operating frequencies. So some other best practice routing tips to ensure controlled impedance. You want to maintain uniform trace widths to ensure consistent characteristic impedance along the transmission line. You can gradually taper down the traces. When you're changing the trace dimensions, you can opt for thicker traces for lower resistance and improved current carrying capacity. And you can maintain, if you can, a 3W spacing between traces to minimize crosstalk and ensure consistent impedance.
And I will share my screen. So we're going to talk about how we might use a VNA for some PCB analysis. And before I do that, I just might want to mention one thing. As I was listening to Amit talk about PCBs and transmission lines, I know that when I do a microstrip or a coplanar waveguide transmission line, I focus on the transmission line on the top itself, and I tend to not think about an awful lot else. But if you think about the RF current flowing through the microstrip or the strip line or whatever we're talking about, there is an equal and opposite current flowing in the ground plane beneath it. So if you have your microstrip with signal flowing left to right, there will be a right to left flowing current on the ground plane directly beneath that. So what's the implication for that? Well, if you cut through that ground plane with a trace, suddenly the return current has to go around that trace and it can no longer flow directly beneath the transmission line. So do keep in mind that your transmission line consists of two things, the trace itself and the ground plane beneath it. So I will continue. Let's talk about VNAs. And let's, oh, before I get too far along, I should introduce myself. I'm Brian Walker with Copper Mountain Technologies. I'm subject matter expert for the company. I've had 40 years of experience in RF design and have extensively used vector network analyzers along with a lot of other equipment. I joined Copper Mountain Technologies about 6 years ago. Before that, I was with various companies, including Motorola. So got quite a bit of experience, and I can say that Copper Mountain Technologies has been around for about 13 years now. And we make USB VNAs, and they're great gear. I can say this after having studied them extensively. We make really good gear that we can verify with our ISO 17025 certified laboratory here in Indianapolis. The gear is manufactured here in Indianapolis, and so we're a fully American company based in Indianapolis, Indiana. So I'll go ahead and continue. So what can be measured with a VNA? Well, we can look at the transmission line insertion loss, its return loss, its characteristic impedance, and in particular, we might be interested in looking at the impairments along the line, connectors and vias and trace-to-trace coupling and the interference that might cause. So here's an example of a simulation where I have a 2-inch long 44.25 mil microstrip trace on 20 mil Rogers 4350 material. The 4350 material is quite good. It has I think a loss tangent of 0.002 or 3 or something like that. So the loss is quite small. And you can see that at 12 gigs, it's only, is it 0.6 of a dB. So the loss looks good. The return loss looks pretty good. So I got the width of that microstrip trace down pretty well. I actually used the calculator from Sierra Circuits to get the first guess on the width. And I don't think I even changed it very much after I did the CST simulation. So it did a good job. It's interesting to look at the bumps. We're always used to seeing the bumps and the return loss. Where do those come from? Well, my simulation has the 2-inch long trace. It has a port on one side and port 1 on one side, port 2 on the other side. There is a small reflection as the signal leaves port 1 and enters the trace because the trace is not perfectly 50 ohms, it's close. So there's a reflection back into port 1 from there. Then the signal traverses the 2-inch long trace, sees port 2, and there is another reflection as the wave encounters the characteristic impedance change from the trace to the port. And so there's a second reflection from port 2, which goes back to port 1. Those two signals add together and create an interference, both adding and subtracting at different frequencies, as you see here. You can actually look at this and measure the frequencies between the nulls or the high spots. And knowing the velocity factor of the signal on the board, how fast it's moving, you can actually calculate the length of the board. So this actually tells you some interesting things just by looking at it. Connectors. I said that we're going to have reflections. My simulation has these simulated connectors on it. It has an SMA connector, and it has a little flat pin. This is actually modeled after an SMA that I got from a mechanical drawing of it. So it's important to get this construction done properly. How do you launch from the SMA to the PC board? Well, let's focus on the return loss measurement. Insertion loss is important, but if the return loss is optimized, remaining losses are due to dielectric and copper loss, and that really can't be changed. So choose a connector with good specifications and physical properties. It's possible that you might just jump onto one of those distributor sites and pick an SMA connector which looks good. But if you don't look very carefully, I've seen SMAs that are only good to 3 gigahertz. And if you're going to 12 and higher, those really won't do very well for you. For your board, choose a core dielectric media with acceptable properties and thickness appropriate for the connector, and we'll get back to that. The core dielectric is important. There are companies making lots of different PCB materials. You have your Duroids, and you have Rogers with their RO 4350, RO 4002. Those are all good materials for RF design. Design your transmission line will have, when it have good return loss and no parasitic resonances. So these are things to watch out for. So it's worth mentioning that an SMA connector with a PTFE, Teflon dielectric, is normally only good 12 gigahertz, but recent improvements have pushed them up to about 18. So check the data sheet. Some SMA connectors are only rated to a few gigahertz. 3.5 millimeter connectors, on the other hand, have an air dielectric and are usually good to 26.5. Then, of course, people ask, well, can I go above 26.5 gigahertz? No, you really can't. If you get to about 27.5, there's a mode, and there'll be a big dip in your response. So 26.5 is it for a 3.5 millimeter connector, to my knowledge. So a connector with a small flat pin is usually best, as shown here. They do make these with round pins. I think they're easier to manufacture, but it does make it harder to solder to the board because the contact with the board is smaller, and you get more parasitic capacitance from the stray E fields due to the kind of larger cylindrical pin versus a flat one. Do avoid connectors with shoulders. As you see the little red circle here, this connector has a shoulder. I don't know why, but it prevents direct contact between the connector face and the PCB, leaving an air gap, basically where the pin itself goes through a little bit of air before it touches the trace on the board. And that's just not good. Now the RF core material, the first dielectric layer, has to be thick enough to prevent the RF ground from shorting to the connector center conductors. So as you can see here, the pin is touching the trace, that little trace is tapered. And you can see that the cylinder of the center conductor on the face of the connector is actually much larger than the pin and extends downward. So if you chose the core thickness to be maybe 10 mils, it would probably short against that center conductor, and you'd get very terrible performance. People think that I need a very, very thin dielectric layer to minimize loss. Well, maybe you do, but you can't hook a connector to it very easily. Unless you pull away the ground, people have mentioned that. You can do that. You can pull away the ground on that ground plane layer so it doesn't make connection. So you need ground plane stitching for a coplanar waveguide with ground. So there's, you can sort of see underneath this, there is another ground layer. So the vias stitch alongside the transmission line gap on each side. They're placed as close to the gap as is feasible. You don't want to have manufacturing problems with the PC board such that you get little whiskers of copper that break away and short out against the trace. But put them close. But talk to Sierra Circuits if you have any questions about how close you can put a trace to the edge of a copper run. Choose a via pitch so that the sides of the holes are less than a quarter wavelength at the highest frequency of interest, and in fact, much less than that if you can. I mean, you really want those to be maybe a tenth of a wavelength from the side of the hole to the next side of the hole. So what does that tell us? You could use very, very small vias on each side stitched close together. You can, but you don't really need to. You can use fairly large vias and just make sure that from the side of one via to the side of the next adjacent via, that gap is what you want it to be. So, at 20 gigahertz in RO 4350, a 20 mil via pitch should be like 80 mils or less. And that might seem like a lot, but it actually works just fine. It turns out that in this particular design, the stitching all by itself is not acceptable. And there's a reason for that. You know, perhaps if I had more vias, like twice as many, it wouldn't be a problem. But it turns out that there's some feeding of the ground planes on each side. Some signal leaks from the transmission line between the vias and excites the ground planes. And at some frequency, those ground planes are quarter wavelength, and then they resonate. So in this case, I modeled this, and there is a resonance of 7.1 gigahertz. So that resonance will cause you a dip in the insertion loss of your trace, of your transmission line. So what do? Well, you add more rows of stitching vias to the board to cut through that resonant area so that it can't resonate. It'll still resonate at some point, but you'll push it high enough that it doesn't matter. You can also increase the number of vias stitched alongside the transmission line, and that will reduce the amount of coupling to the ground planes itself. So it's interesting to think about what's actually going on when you feed a circuit board from a connector. The pin, well, the center pin of the coax is round, and it goes from a completely coaxial environment, and you can see the field distribution on the upper left, the electric field distribution. It's quite symmetrical and circular, or radial. And but if you look along the coplanar waveguide, bottom right, that heart shape there, the fields are completely different. There is coupling to the side grounds, and there's coupling through the dielectric to the circuit board ground beneath it. So you do have to transition from this totally radial to this heart-shaped pattern. So if you think about it, anything you do is going to cause some kind of reflection, because making that transition is difficult. All you can do is do a gradual as possible transition, such that the fields aren't quickly changed or distorted. I'm just trying to give you a feel for what's going on here, and I think maybe it helps you understand what's happening. So near the face of the connector, there are these excess fields. So you can see that right up against the connector, the heart shape is distorted, and it looks like it's partly radial upward, and it still has kind of the heart shape of the later pattern which develops. So this amounts to a lumped capacitance basically at the interface, and it lowers the characteristic impedance at that point. So finding the locations of reflections on a PC board, that's extremely helpful. And the design can be improved if the source of the problem is well known. So is it the input connector? Is it coupling to some other trace? Is it via transitions? Sometimes you have to move an RF transmission line from the top to a middle layer and then back up again. And so you're going to do that with vias. How do you design that? How do you design that transition using what kind of via pattern to minimize the impairment of the design? I'm not going to go in that today. That's probably a good topic for some other day. But we can optimize the launch. So with a Copper Mountain Technologies VNA, you can use a time domain analysis to look at your fixture. And as you can see, I have this is a transmission line with a connector on each, an end launch connector on each side. And what do we see here? This is return loss versus time. And the big bump on the left-hand side is the initial launch from the circular part of the connector to the just the beginning of the PC board. The next little bump is basically the pin laying on the circuit board, and a little bit of probably a little bit of transition to the face as well. Then you get into the circuit board itself, and that return loss is quite good. And then you see a similar thing going on the right-hand side. So this tells me that the return loss of my system, if I took this whole thing as a system, is completely determined by the connector. So the trace is fine. I could optimize the trace all day long. It's not going to help. So what can I do? Well, I can use the impedance conversion and get a little bit more information. Now here, instead of return loss, you know that the return loss is just or the reflection coefficient is related to the complex impedance. That is, the reflection coefficient is Z minus Z naught over Z plus Z naught. And I can solve for Z because I know Z naught and I know the reflection coefficient from the previous slide. And so I can generate a plot of characteristic impedance. The VNA does this automatically, so it shows me what's going on. So I can see here that I start out at 50 ohms in the cable. I get to the connector. There's a little upward bump, probably where the pin is just exiting the flat face. And then I get the interaction of the pin to the face, and I get a lowering of the impedance. It's not very much, but it's down 0.6 of an ohm. And then I get into the trace itself, and it's pretty close to 50 ohms. And then I got something similar going on the other side. This tells me a little bit about the launch, and maybe what can I do to improve this? Well, maybe I could taper the trace, and people do this, and people do things with the ground underneath it to try to improve this response. So the geometry of the taper is kind of impossible to determine without EM simulation or some trial and error. Maybe get out your X-Acto knife and try it yourself. But some methods like this can improve the total return loss performance. Do note the PCB trace should go all the way to the edge of the board as much as possible without copper pullback. I know the PC board manufacturers hate this, but if you have too much pullback, then you have a pin that's just sitting on dielectric with no copper, and that looks inductive. So copper gap at the edge of the board adds this lumped inductance and limits the usable bandwidth of the board. So this is something to think about and negotiate with your circuit board vendor. What about trace to trace coupling? These days we're running traces right next to each other, and it gets to be quite a problem sometimes. Let's say you're doing an FPGA design and you have multiple lanes at very, very high speeds of differential lines, and you want to know, are those lines talking to nearby lines? Well, you can measure that using a multi-port VNA. You may know that a VNA makes unbalanced measurements, but you can hook each port to one line. You can take, for instance, you can take 4 ports and hook to a differential pair. That's 1 port for each line for each side. And then you do go into the VNA menu and ask it to do the differential calculation. And it'll give you STD11, STD21, and show you all the differential parameters. So you can use that to measure the health of your differential line on your circuit board. So if you're doing high-speed FPGA design, you want to know what's going on the board. You want to know whether it's what's the isolation of the traces, what happens when it enters a connector and comes out the other side. You can measure all that, and you can use a time domain function to see exactly where it is. And you can kind of poke at it and determine whether it's a capacitive or inductive, and what could you do to try to improve your design. So the time domain function is very, very powerful. It comes standard on all of our equipment except for our M series. And of course, there's our 16-port VNA, which is available for making measurements of many differential pairs if needed. So I'll just introduce the S5180B. This is our 18 gigahertz compact 2-port VNA, and I'm going to use it for our TDR demonstration today. It has a pretty good dynamic range, 130 dB typical. Measurement speed is pretty darn good at 24 microseconds per point, and the output power at plus 10 dBm is enough for most applications. This also comes with pulse modulation as an option, so it can be used for developing a power amplifier on the bench when you don't want to hook it to a huge heat sink and a fan. You can excite the PA in pulses and have an average power in the milliwatts, even though you're exciting it up to several watts. So this is a pretty darn good VNA at a great price. So you can check this out on our website at www.coppermountaintech.com. All of our VNA products are listed there. That's all we do, VNAs and the devices you need to calibrate them. I did mention that we can do differential measurement. You can do that with a 4-port VNA or the 16-port VNA I mentioned earlier. The 4-port VNA will do a single pair. The 16-port VNA will do 4 pairs. But do keep in mind that using trace math, you can use a 2-port VNA to make a differential measurement from one side. How is that useful? Well, you can measure from one side and use a time domain, and you can look at a differential line that's moving along a board, goes through a connector, comes out the other side. And so this 18 gigahertz VNA, 2-port VNA is sufficiently prepared to make time domain measurements on a microstrip, a strip line, coplanar waveguide, or a differential line. So it has everything it needs to make those kinds of measurements. I'm showing in the bottom right-hand corner the trace calculator. I'll show that in the demonstration. That S11 plus S22 minus S21 minus S12 divided by 2 is the formula for deriving differential return loss from the 4 S parameters that you're measuring. Yeah, okay, so next. So let's look at this. Let's look at a time domain measurement, and then we'll wrap up for questions. Go ahead. Okay, yeah. Let me stop sharing this. And turn on the camera. And I'm going to share, so here is the VNA. Yeah, there we go. The bottom was covering it up. So this is the S5180B VNA. And on top of it, I have an automatic calibration module. And this is my test board. It has a 100 ohm differential line on the top. And on the bottom, it has an interesting line, a microstrip line with an impairment. It's 2.5 inches of 50 ohm line, about 1 inch of 25 ohm line in the middle, and 2.5 inches of 50 ohm line. I don't think you can really see it in the camera, but take my word for it. So we'll measure first the 50 ohm line with a 25 ohm impairment and see that we were able to see that with the VNA. Let me share the screen of the VNA. So now you're seeing the output of my VNA screen. I'm looking into the automatic calibration module, so what you're seeing on the screen is not terribly meaningful to begin with. But let's do a calibration. And so I have this set up for 9 megahertz to 18 gigahertz, 2000 points, and 10 kilohertz I have bandwidth, which is just fine. The output power is 0 dBm, which is adequate for our measurement here. I've chosen the start frequency and the start frequency and the number of points judiciously. The stop frequency divided by 2000 is 9 megahertz. That means that I have harmonically related measurement points, essentially 0, 9, 18, and so forth, all the way up to 18 gigahertz. Now, I'm not actually measuring 0, but I can interpolate it based on measurements around it. Why would I want to do that? Well, because in the time domain mode, we do a special trick. We take these harmonically related points and we flip them around 0, and we generate negative frequencies, -9, -18, -27 to -18 gigahertz. And we populate those negative frequencies with the complex conjugates of the reflections that we measure in the positive domain. And then we take the inverse Fourier transform of that. Now that sounds like a lot of trouble, but the reason we do that is because if you take the inverse Fourier transform of that symmetrical system, you end up with a real result in the time domain, which is what we want. It also gives you twice the resolution in time that you would otherwise get. And it also gives you access to the low pass step mode, which lets us see characteristic impedance. So lots of reasons for wanting to do that. And that's the way we have this set up today. Okay, so let's go ahead and calibrate. I'm already hooked up, ready to calibrate. So we'll do that thing. Calibrate autocal. We're going to do a 2-port auto calibration. Give that a moment. And it's finished. So if you do have a VNA, you will want to have an automatic calibration module. It greatly simplifies the calibration process, eliminating many errors that you might otherwise create. And it gives you superior calibration compared to a mechanical calibration kit. The artifacts inside the automatic calibration, that's the load, open, and short, and through, are data-based. So the result is that instead of assuming that you have a perfect 50 ohm load as you do with the mechanical calibration kit, you tell the VNA exactly what the 50 ohm load is based on the database that's inside the ACM. The result is a much more accurate measure. Okay, so now I'm hooked to the transmission line with the 25 ohm transmission line in the middle of it. And I'm going to go to the time domain. We're going to go analysis, time domain, turn it on. Let's use units of seconds. I don't want to, I can change this to units of length if I know the velocity factor of the board and I could enter that, but let's just keep it simple and I'll leave it in seconds. The measurement is naturally a two-way measurement there and back for a reflection, but I'm going to divide that by 2 because that's all I'm interested in is out to the point where things are going on. I'm going to start at 0. Happen to know the board's about a nanosecond long in time. So now I can see here on my screen the return loss versus time or distance if I entered all the information. So what does this tell me? I'm seeing about minus 40 dBm or dB for the S11, the return loss along the 2.5 inches of 50 ohm line. This is quite good. And then when I get to the 25 ohm section, you can see that it goes to about 10 dB return loss, which is pretty awful. After the 25 ohm line, we see this shoulder and it kind of slopes down. You would think that it would drop right back down to minus 40 and continue across. Well, it would do that, except for one issue. The 25 ohm section is reflecting quite a bit of power back to the source. So the incident power is reduced by the reflection that it sees first, and it shadows everything that happens after it. This is a common thing that you have to be aware of in the time domain analysis. So if you have a large reflection, everything after it is going to be not quite as accurate. It'll be shadowed by the first big reflection. A series of small reflections are not as big of a problem. Let's go a little further. We're looking at return loss here on the screen. Oh, and I should mention this. Does this mean this minus 40 dB? Does this mean that the return loss of my transmission line, the microstrip, 2.5 inches of it, does it mean that it's really has a return loss of minus 40 dB? No, it does not. What it means is each point along here is a small slice that is being turned into the reflection coefficient of that tiny little slice of the microstrip has a minus 40 dB reflection coefficient. So the actual return loss of this 2.5 inch section would actually be the integral of this information here, if that makes sense. So this is looking at little time slices along the microstrip, and it's telling me what the reflection at each of those little slices is. Let's turn this reflection into characteristic impedance. We can do that by going to conversion and turn that on. And we're going to choose the reflection conversion to Z. all this does is it solves gamma equals Z minus Z0, Z plus Z0 for Z, because we have gamma. And go to linear magnitude, 5 ohms per division, 50 ohms. And now we see the 50 ohm transmission line, which looks pretty good, the first 2.5 inches. We see the 25 ohm section in the middle, and then we see kind of the 50 ohm things that follow it. But of course, the shadowing of the 25 ohm section is causing us to have some error here on the right-hand side. What's this little bump on the left-hand side? That's the connector. You should be used to that. And the impedance is a little high, indicating that it could use a little more capacitance to ground. And we could probably do something to improve that. You could get in there with an X-Acto blade and try to fix that, or some copper tape if you're a real hands-on person, or you could turn right to an electromagnetic solver and try to fix it. So this shows us the time domain measurement that we just made on this board. What I should have shown actually is what does it look like just without all this fanciness. Let's turn the conversion off. Let's turn the time domain off. And let's go to log mag again. And let's add a trace. Okay, so now we're looking at, these are not lined up. We'll line these up. So now we're looking at the insertion loss in the cyan color and return loss in the green. This is terrible return loss. I mean, this is minus, what is this, -5, -7, and the insertion loss is suffering as well. So that 25 ohm section is doing some real damage to the response of the transmission line, as you would expect. And the time domain allowed us to find exactly where the problem was. Now, I could actually look at it and see, but sometimes these problems are a lot more subtle, and the time domain analysis will really bring this out for us. I will do one more trick. We're looking at a single line right now. Let's look at a differential line and use the trace calculator to do time domain of a differential line using 2-port VNA. Along the top of this board is a pair of 50 ohm lines that are spaced closely together such that it forms a 100 ohm differential transmission line. So I'm going to measure from one side, leave the other side open. Won't be able to do normal frequency domain measurements this way, but I can do time domain and just look through it. But I'll have to use a trace calculator to turn my 2-port measurement into a differential measurement. And that is very easily done. Okay, so I'm hooked to, I have ports 1 and 2 hooked to one side. I'm going to go back to one trace, and I'll go to the trace calculator, which is built into this menu up here. More, calculator, advanced, and here we are. So I'm going to calculate SDD11, which is the differential insertion or return loss. And I happen to know, everyone should have learned in their 2nd grade differential class, the formula is S11 plus S22 minus S12 minus S21 divided by 2. And that is the calculation for SDD11. And the title will be put up in the display. So here's my my trace name is changed to SDD11, and I'm now measuring the return loss of that trace. It looks, oh, of course it's bad because it's open. So we have to go, we really can't see anything here. We have to go to the time domain. We'll turn that on, and by golly, it looks pretty darn good. I can see this 30 dB return loss. I can see what's happening with the connectors on the left-hand side. see what's going on the right-hand side. I have to do a little trick here. Because the transmission line's 100 ohm, the ports are 50. The VNA doesn't know this, so it gets a little confused when it tries to put this together using the conversion. So I had to tell it to use 100 ohms. So I'm going to turn this on, and I'm going to go to linear magnitude, and I'll do 5 ohms per division, 100 ohms center, and now we're looking at the differential characteristic impedance of those two lines, and we can see again the transmission, the connector has a little bit of a bump. What's this little business here at the beginning? That's where the traces are actually you're kind of fanned out in a V shape before they come together. And then they come together, and the impedance becomes this about 105 ohms. And then same kind of things happening on the far end. And of course, it's open, so the characteristic impedance becomes undefined. So I'm using a 2-port VNA to make a differential measurement, and it was very simple to set up. And that is the end of my demonstration.
So we're going to talk about briefly some series trace terminations, parallel trace terminations, and some routing, and then I'll pass it over to Brian. So for series trace terminations, this involves placing terminating resistors between the driver and the transmission line. The resistor is placed close to the driver's side, and its value is chosen such that the combined impedance of the resistor and the driver matches the trace impedance. And here we have shown one instance where the driver impedance is 23 ohms and the line impedance is 50. To match these impedance, we implement a series resistor of 27 ohms near the driver end. And you have also parallel trace termination.
So can we do the demo?
Sure. Just give me a sec. So parallel trace terminations involve placing a shunt resistor in a parallel with the receiver. This matching resistor absorbs all reflections at the far end of the transmission line. And you can connect the parallel resistor to the power supply or ground plane depending on the IC's internal circuitry. And then you can do the serpentine routing, and it really allows for signal synchronization. And you can see that if you can do a 3W, that would be best. If you can't, then that's understandable. It's designed to getting more dense, but just understand that this is an important option.
Okay, everyone, you should see a few questions on your screen. If you can answer. And I'm gonna leave the poll on during the Q&A, okay? So we can start answering the questions. Attar, Vandana, Hemnandan, we have a couple of questions at the top about the calculators. Do you see them, Attar?
Yeah, the first question is about the trace calculator from your side. Why does the calculator not include the option for like coplanar waveguide?
Attar?
Where are the questions?
In the Q&A, open the Q&A in Zoom next to share.
I'm not able to see anything. Okay, Q&A. Okay, there is a separate. Just a minute. It's becoming difficult. Okay, Q&A. Okay. Why does the calculator not include an option for K? The coplanar impedance calculator for coplanar is already there.
I don't understand. What is the
So
question?
that's the bandwidth calculator is talking about.
Hmm?
Bandwidth rise time trace calculator.
Yeah, that is okay. It's still the same. It will still be the same. Okay. What is the next? How does conformal coating impact insertion loss? Any kind of coating will increase the loss. Okay, yeah, every coating, conformal coating, whatever is the material, it will have a what do you call a loss tangent. Therefore, it is going to increase the loss. All right.
I thought you missed a question at the top from Luis Perez about the calculator.
Does the calculator results have been correlated with? Yes, they have been. They are the calculator results in most cases are within plus minus 10% and also within plus minus 5%. Okay. The calculators are, let us say, the results are comparable to the best of the priced control characteristic impedance calculators available in the industry like Polar and Hyperlinks and all. Okay, all right. With inic finish, how does nickel loss compare with solder mask loss? Depends upon the solder mask loss is definitely much more. Okay. Yeah. What else? We put a thermal pad on top of the PCB in order to maintain on top of the PCB to maintain the bore temperature. How does this affect the high-speed signal integrity? If the thermal pad is a ground, I mean, depends upon the thermal pad, how far it is from the signal lines, etc.
Atar, there's someone in the background making noise. Can you ask them to stop?
Just let me move somewhere else. Something is happening in the backyard.
I think while Atara is doing that, I can talk to one of
Yeah.
them that's asking that question for me,
Please do, please do.
where he's back.
Okay, we put a thermal. So thermal pad is generally depends upon the location of the thermal pad in reference to the lines, but the thermal pad is a vertical thing. Okay, and normally if you have a signal plane and you have a ground plane next to it underneath the plane, covering the entire signal transmission line, say signal line with, on both the sides of it pretty broadly, completely, then therefore there should be no impact of that. Okay. Does the edge of a square wave signal change during transmission over an electrically long line? Yes, definitely. Some amount of ringing and other things, etc., will take place. Yeah. Okay. The square wave requires a whole lot of, Fourier frequencies to be constructed of, and therefore it will get affected. So a totally square wave with very sharp edges, of course, is very difficult to achieve in actual practice. Okay. That is why all waveforms at very high frequencies are never with a very sharp edge. They have a rise time and they have a fall time. Okay. Which is preferable, a 50 ohm output and a 50 ohm line, or a 25 ohm output and a 25 ohm line? I don't know, 25 ohm output. Normally 50 ohm is the industry standard, and all the devices, all the communication protocols, they're all primarily using by and large 50 ohm. I have rarely seen a 25 ohm. Have you seen anything like 25 ohm? Sir?
I have seen lower impedances from certain drivers. Like I think the one that Amit mentioned was
Oh, you mean the source impedance of the driver? The
I think-
output impedance of the driver.
yeah, I think the question is basically if you had a 23 ohm driver, you could use a series terminating resistor. You could use
Yeah.
25 ohm, you could use a 25 ohm line though and have.
No. Most
less
of the
than
drivers will have a much lower impedance than 50 ohms. Yeah,
Yeah.
that is true. I mean, most drivers, and you generally have some kind of a series 22 ohm series things to avoid the ringing and all that. Basically, to avoid the reflection at the source end. Okay.
But you could also have a 25 ohm line. There's nothing wrong with that.
Yeah, there's nothing wrong with that.
Nobody does that.
No, nobody does that because of the fact that the receiver. See, nowadays, most of the ICs, receivers, and all those kind of things, they have a built-in impedance termination, okay, which you can program and all that stuff. And many of the, it depends upon the communication line, what you have at the, destination, okay. If you are just having an interconnection between two, what do you call, between a source and a destination internally on the board and without having any effect. But please understand, a 25 ohm line would require a much wider trace. Okay, so it will impinge on your real estate on the board very much as compared to a 50 ohm line. So just be careful on that.
I can take the next question about the via fence. I did say that the vias could be a quarter wavelength apart. That really is bare minimum. And in fact, if you do that, there's going to be some evanescent mode leakage between them. So it really does. It would behoove you to do something less than that. The next one says lambda over 8. That's not a bad idea at all. I've seen lambda over 10. So take your pick. The only trade-off here is are you increasing the cost of the PC board? Because if you're going all the way through the PC board, I've talked to Amit about this. If you're going all the way through the PC board, then you have to use a mechanical drill. If you're going through just one layer, it can be laser drilled, and then that really doesn't cost much. There's no cost difference if you have a bunch of vias. So it's something to think about. Yeah, I think lambda over 8, lambda over 10 is probably a good choice. Because why? You're particularly because of that issue where there was leakage into the ground planes on each side that was exciting them to create a resonance. So that's a really bad news. So yep, lambda over 8, lambda over 10, good choice.
So in case of this is my question down to you on the same thing. When you have a coplanar kind of a structure, to make that coplanar ground on both the sides very, very wide also may not be a good idea many times. What do you have a feeling on that?
Oh, to make them wide, you say?
No, less wide.
Oh, yes.
Because otherwise, if you make it very, very wide, then you will have to stitch, another row of, stitching vias and all that stuff. Yeah.
Exactly right. Yeah, I mean, if you do have a big ground area, you can't just leave it.
You can't just leave it like that. Yeah.
That's right. If you have two grounds, one top, one bottom, and they're just sitting there, they're looking for trouble. They're going to talk to each other. You're going to get waveguide modes between them, maybe, or you're going to get a resonance on the top from edge to
They can
edge.
act like antennas also. Yeah.
Yeah, exactly. So yeah, so if you do have ground planes top and bottom, you're pretty much going to have to stitch them together everywhere,
Right.
to some extent.
And the the more VRs you have on the board, the fabrication cost increases also. That also is important to understand.
Yep.
Yeah.
In the time domain trace, it's asking why is the impedance on the right-hand side not 50 ohms? Oh, referring to the connector example in the slides. I might have had, I don't want to open it and get.
I thought it was related to a connector over there, wasn't it?
Yeah, I mean, I had two kinds of slides. One was in characteristic impedance and the other was in return loss. So in one case, you're seeing the, dBs of return loss and time domain return loss. And in the other case, you're seeing the conversion to 50 ohms. So yeah, those are different different portrayals of the same kind of information. Hope that answers the question. And then when could we use the port extension to move the point of the reference plane measure? All right. And I think the main question is de-embedding versus a port extension. I did do a webinar that talked about this some time back. Port extension simply corrects the phase. It just moves the delay out so that the reference plane delay is where you want it to be, where the zero is where you want it to be. Zero phase, zero time is moved to a specific point by changing, by using port extension. The one thing it does not do, it does not correct or remove reflections. So if there are reflections between the primary reference plane and the point to where you moved it, those reflections are still there. So moving from the end of your cable, say through a pigtail to a circuit board, and if the pigtail has a 10 dB return loss bump in it or something, or a crimp, you'll probably get the phase sort of right at the circuit board, but the return loss will be terrible. You're not really fixing it. The port extension does allow you to remove a linear loss factor. So if you're looking through a piece of cable, you can sort of remove the loss factor. But if there are any reflections of things along the way, it does not correct them. Secondly, one thing which is very important, if you try to do port extension over a wide frequency range, it simply won't work, because anything you look through is going to have some dispersion, and port extension assumes a constant delay. You're just dialing out one delay, and if the delay is not constant, your results will be terrible. And you'll see that when you try to do the port extension, instead of getting a dot on the right-hand side or wherever you're aiming, you're going to get an arc or a bunch of squigglies. De-embedding on the other side, on the other hand, gives you a great response, and it puts the if you're trying to hit an open or a short or whatever you're actually looking at for your calibration, it'll put you right on a short or right on the open, and there will be no arc, there'll be no little squigglies. It'll do a great job. And to do de-embedding properly, you need to actually make a two-point measurement of the thing that you're de-embedding. Or if you can only get at it from one side, you need to use the automatic fixture removal program, which we also offer with our VNAs. Next question, have you used TDR to check impedance of vias? I haven't done that in years, but yes, it can be done. Let's see. The change in dielectric constant in the Z direction from that for the X and Y direction. Well, I think the dielectric, I think you're talking about the effective dielectric constant, because you're no longer going along the top of the board, you're actually going through the dielectric. I think that must be what you mean. Yes, there's all kinds of changes that happen when you go from horizontal to vertical on the PC board. What I have seen is that you would have a central via for your signal, and you would build a radial fence of vias around it to try to create a sort of a coaxial 50 ohm line. It's very difficult to do, and the only way that you're going to pull that off is to do full EM simulation of some kind. So yes, it can be done, and it can be done well, but it's not easy.
Let me add to that answer. We have a reasonably okay kind of VR impedance calculator on our website. And we also have a effective dielectric constant, calculator. Also, the effective dielectric constant in the Z direction can be done. Now, the VR impedance, as closer as you can design your VR to your 50 ohm line or whatever line you are having the VR in, it would be better. So it doesn't have to be exactly the same. I mean, it's very difficult to achieve all that. But at the same time, the closer you make it, the better it is for your signal integrity. Please understand that when there is a VR causes a impedance discontinuity, there is one kind of discontinuity will happen at the start of the VR, and the opposite kind of discontinuity will happen just at the end of the VR. So the time taken for the signal in the VR for this discontinuity, let us say if it is not very significant with respect to the data transfer rates that you are bothered about, then possibly this can be ignored. And that's why you find some literature by a lot of signal integrity experts saying that VRs really do not make a very great impact on signal integrity. But of course, that is in the not the 20 gigahertz kind of range and all that stuff. Yeah. Okay.
Great. I'll take the next one. Where can I find some practical techniques for connecting the VNA ports to traces designed with various impedances on a production PC board needing troubleshooting? Actually, there's some great resources on the Southwest Microwave website. They have some papers on analog connectors and I think some other things. I also wrote a fixture creation paper on you'll find it on our website. So if you go to coppermountaintech.com and look under the technical assets and search for fixture, you'll find that presentation or paper. I forget which one it is. I would say I'll go ahead and take the 300 hertz. Yeah, I mean, it looks like James underneath answered the question. It's all about the wavelength. So at 300 hertz, you would be concerned if the transmission line is a quarter mile long or something.
Yeah, actually, the wavelength will be so large.
Yeah.
Yeah.
So 300 hertz is basically DC.
It is DC, yeah, for all practical purposes. Okay.
Yeah. For time domain analysis, did you manually select the time amount, or is this VNA selected automatically based on the frequency sweep? I actually had to set it. It actually comes up with 0 in the middle and minus time on the left and minus time on the right. And I'm not even sure what it chooses. I'd have to look. But I actually had to zero in on it. And let me make one more comment that the inverse transform that we're doing is not actually an inverse Fourier transform. It's an inverse chirp Z transform. The reason for that is that the inverse chirp Z transform allows you to zoom in on a time domain response cleanly. So you could look at what's going on between 1 and 3 nanoseconds very nicely. Whereas if you did that with an inverse Fourier transform, you did a bunch of points, you got the resolution, whatever you got, but if you zoomed in on it, the result would be chunky. You have a lot of little steps in it. The inverse chirp Z transform allows you to pick the range that you want and have that output from the transform with all the number of points that you've already chosen. Now, it sounds like cheating, doesn't it? It sounds like you're getting something for nothing. And it is sort of cheating. At some point, the error does it becomes significant. So if you zoom in too far, your results will be meaningless. like that guy in the crime scene that says, you know, looking at the video, you know, enhance, and it keeps getting better until you can read the newspaper. No, it doesn't quite work that way. So we do have a method which works quite well, and so but you do have to set it up manually. Is there any reason I use the trace calculator versus fixture simulator during the differential pair measurement? Yes, fixture simulator is only available on our 4-port VNAs. So there is no fixture simulator on the 2-port VNA because, well, I don't know. I guess I'm not sure why. Normally, if you wanted to do a differential fixture simulator, you really do need a 4-port VNA because you want to look at both sides. All right, I'll let.
What CAD PCB software do you really recommend? I think Allegro, we prefer Allegro, Altium are, I think, the two of the most popular industry softwares. Of the KiCad, of course, is getting some kind of a, popularity because of free software. But among the professionals, I think mostly Allegro, Altium are, especially in United States, are very popular. Yeah,
I would vote for Altium. Love that software.
true. There are some diehard Allegro guys who do not like Altium user interface. Brian, let me tell you that. Okay. But Altium is very powerful as well. Yeah. I'm working on CPW transmission lines in silicon substrate with 3 layers silicon, SiO2 and metal layer as trace line, but I'm not able to find the correct dimension of the trace width and gaps. You're talking within the silicon substrate, 3-layer silicon and a metal layer as trace line. Oh, this is because of the dielectric constants of silicon dioxide and all that, which are not available. I am at a loss to understand why there are, specific calculators, but we will definitely try to take care of the silicon substrates also. A good suggestion. Thank you.
I think the issue might be that the calculators generally are based on I think Wheeler formulas. They kind of falls apart if you go to certain extremes of mechanical dimensions. And
Right.
so that might need to be done in a planar EM simulation like the CST or an ANSYS.
Right. ANSYS, yeah, you're right. I mean, but I have a feeling that people who use silicon dioxide and these kind of things, they have a special calculator for that. That's what I'm not able to put my finger on that.
Okay.
Okay.
So I'll take the next one. Software mirrors the frequency domain for the negative frequencies. Do you just interpolate the DC, then perform the actually inverse Z transform, or do you leave it out and use the actually measured and mirrored data in the IFFT? No, the DC term is basically you can fill it in by hand. It allows you to do that, or the software figures it out. So if you're looking at an open, as I have been doing, the DC term would be 1. That's open, a complex 1J0. And so that has to be filled in for the DC term. If it were short, it'd be -1J0. If it were anything else, you'd have to kind of know what that was and fill that term in. But it's either open or short for the most part. So that has to be filled in as the DC term, and you can enter it or let the VNA figure it out. Yeah, so that's what's happening there.
Thank you very much. Oh my God, that was a very long Q&A. Thank you everyone for asking questions. Thank you so much, Amit, for the presentation, and Brian for the presentation as well and answering questions. Thank you, Atta. Thank you, Vandana, for the demos. I will send you the slides and recording this afternoon, and have a great day.
Thank you, Brian. It was a wonderful presentation from us.
It's been great talking to you. All right, well, it's been fun, and thanks everyone for attending, and I hope to do this again soon.
Thanks, guys.
Sounds good. Bye, everyone.